Hello, welcome back. In this segment, I will explain how to do graph-based reachability analysis. Suppose you have some dependency graph. Nodes could be name of functions or files or whatever, and there is some dependency from one node to another node. Then there is a path from that node to another node. For example, 1 depends on 3, then there is an arrow mark from 1 to 3. The question is, let's say, as an example, show me what are the different ways I can reach node number 4. So how can I construct automatically a subgraph which will show me all possible ways I can reach node number 4. I'll show you how to answer such questions using basic relational algebra. The first step naturally is to represent the graph in a relational model, and graph and relations go hand in hand. So we can easily visualize rel underscore transitive closure is computed on the input relation. Okay, you see a lot of pairs now output. Okay, let me explain one pair. Let's say 1, 5. Okay, why do we have 1, 5 in the output? For that, we need to visualize the graph again. You see there's a path from 1 to 5, right? Through, for example, 1, 3, 3, 4, 4, 5. That's the reason why there is 1, 5 in the output of the transitive closure. So transitive closure means all possible ways to reach any pair of nodes that will be part of the transitive closure. So we need to compute transitive closure oftentimes. So I compute it once and save it to a file. Let me show you how to do that very quickly, and then we move on to the reachability problem. So all you have to do is save it to a file. Let me call it demo underscore trans.rel. Now the file is having the transitive closure of the demo. I need to show you a couple of more operators before we can do the reachability analysis. So given a relation, I can ask for a few things like the first column of a relation, that's called the domain of the relation, 1 to 4, because 1 to 4 occurs on the first column of the relation. Okay. We can also ask for range of a relation, that means the second column. Okay. We can restrict a relation to a subset. Okay, let me show you what it means. Suppose I would like to restrict the relation to, just as an example, nodes that end with, say, create a set with 2 elements, 4 and 6, and then I can restrict my relation, right? Let's say restrict the range of the relation. The relation is demo.rel to 4, 6. That means if you look at the output, right, the second column of the output has only either 4 or 6. That is the reason for range restriction. We can also restrict the carriage of a relation. Carriage means both left-hand side and right-hand side to a particular set. If you do like this, there is no output because the pair 4, 6 is not part of the relation graph. Okay, that is the reason you had empty. But if I were to put here, say 2, 4, and 6, right? Now I get 2, 6, 2, 4 because there is a pair 2, 6 on the graph. There's a pair 2, 4 on the graph. That's the reason why carriage restriction is restricting both the domain and the range to a given set. Okay, so this is what we need. We can now very quickly find out reachability of the graph to the node number 4 that we are interested in. Okay, create a set 4. Set just means the set has only element 4. Yeah, nothing interesting so far. And then I can restrict the range of the transitive closure. Remember, I did the transitive closure of the original graph to 4. That means I'm interested in all possible ways 4 can be reached. Yeah, so these are the only 4 different ways I can reach number 4 on the graph. We are not done yet. What we need to do is we need to show how to reach 4. Okay. What is next thing we need to do? We can find out both the domain and the range. That's called the carriage of the relation. Okay. So carriage of the relation is just a set, which is 1, 2, 4, 3 in this case, because if you look at the output of the previous command right here, you just select set of all elements present here. So 1 is here, 3 is here, 2 is here, and 4 is here. That's the reason you get 1, 2, 4, 3. Okay, order doesn't matter. 1, 2, 3, 4 is the output so far. Once you get the carriage right, these are the nodes that will lead you to the number 4. Okay, now I can go back to the original relation, right, and restrict the carriage of the original relation. Carriage of the original relation is demo.rel to 1, 2, 4, 3. Okay, why would this work? This would work because we know the only way to reach number 4 is involving the nodes 1, 2, 4, 3. Okay, no other possibility exists. So from the original relation, we are going to select all pairs that would involve these 4 elements, 1, 2, 4, 3. So now you have the relations that are going to help you to reach the node number 4. Okay, so you can just now copy and paste this to your graph visualization tool and visualize it. This is basically raw data. Let me just copy this, right? Go back here, for example, one moment. You have 2, 4, 4, 1, 3, 4, 1, 3, right? There are 4 nodes, 2, 4. Yeah, obviously you reach number 4 from 2. From 4, 1, yes. And then 1, 3, and 3, 4. Of course, this is a cycle. That's the reason why you get 2, 4, 4, 1, 3, 4, 1, 3. Remember, 2, 6 is gone, 4, 5 is gone, because we are not interested in anything other than all possible ways I can reach number 4. Okay, now we can visualize this easily, right? I just cut this thing here and put it here. The original graph will disappear, of course, and I just have to replace for this particular tool space by arrow mark, and now I should be able to see the graph. Yeah, you see here, I have the graph. Now the 2 nodes that I talked about earlier disappeared because they are not involved in reachability to number 4. Okay, so that's basically how you can do simple reachability analysis by composing basic queries using relational algebraic operators like performing transitive closure, extracting the first column, that's called the domain, extracting the range, the second column, restricting the range, restricting the domain, restricting the carriage. These are the different operators that I have just very briefly showed to you. This is how you can create reachability graphs. Okay, thank you very much for your attention. That's all.